This code here is for the stopwatch module at the core of our design. The inputs and outputs are a start-stop signal tied to a button on the FPGA, a program signal tied to a switch that governs whether the stopwatch is in its programming or running mode, a clock signal connected to the system clock, an up input. If this signal is high, the stopwatch counts up, and if the signal is low, the stopwatch counts down. There's a reset input tied to a button on the board, an increment signal that increases the program time tied to a button on the board, and the minute signal governs the mode of programming. This outputs a 39-bit time signal to a wire that passes into other parts of the machine, and a 0 signal that passes to the time module. This design has a number of 39-bit registers that encode various time values used for its functionality, and the stopwatch itself has been implemented as a state machine. The states have been encoded using a one-hot encoding scheme to save on logic size, and those encodings have been saved in parameters. The counts are initialized in this initial block with the hard-coded time HCT register corresponding to a hard-coded countdown time of 1 minute. This has then been implemented as a hybrid Moore Mealy machine where all the state transitions occur at the positive edge of the clock in this always block. And however, many of the outputs are, in the nature of a Mealy machine, a function of the input. So this defies easy categorization. This if statement here governs the 0 signal that passes to the sound module. The implementation then takes the form of a case statement in which the counts and the outputs and the next state change as a function of the inputs. And then at the bottom of this block, using blocking assignments, after the assignments have been made, the present state is assigned to the next state and the machine rolls over the next clock.
So this is the finite state machine for my 7-segment displays. It takes an input number and the decimal points you want to eliminate. It has a common cathode between all of the displays, which are the 7 segments that are eliminated, and an anode, which specifies which of the 8 displays you're driving. The input number is converted into minutes, seconds, and milliseconds in this module, and then converted into BCD in this module. That number is then divvied up into 4 different numbers, and decoded into the individual lights on the FMT LEDs in this module, and then it cycles through all of the different LEDs, all of the different 7-segment displays rather, and drives the number to each of them with 1 millisecond in between.
In this leaderboard module, we have a timing input that is used as part of an always block in order to alternate between the 2 modes for our functionality, that being the slow mode and the fast mode. And basically how it works is whenever the time in is of great enough value to replace the rankings, it does so. As in here, it will replace the number 1 ranking if it's greater than number 1, number 2, and number 3, and it will send a signal corresponding to the music to be played specifically for that specific change in rank. We also have another always block that is used to display on the LEDs what mode and what rank we are in. In this beep module, or rather the sound module for our overall machine, how it works is that it takes in 4 input values, a clock, and outputs to a speaker that's connected to the audio jack on the board. 3 of the values come from the leaderboard module, and 1 value comes from the stopwatch module. Essentially, the way it works is every time one of the values changes, it produces a specific sound for that specific change in value. This allows for different sounds to be played for each changing of rank in the leaderboard module to indicate that a new high score has been achieved, or when the alarm clock reaches 0 to indicate that the alarm clock is done. This is done through the use of various variables to allow for, in conditional statements, to allow for those specific sounds to be played, and a time-lasting variable in order to allow for a 1-second duration of sound.
This code here is the top-level module in which we instantiated the various constituent modules that made up our design. As you can see here, there are a variety of signal declarations, assigning the I/O signals of those modules to the wires and registers declared here. This module functions correctly in simulation, but the design generated in the bitstream by Vivato's synthesis tool did not correspond to the correct implementation and therefore introduced timing errors that rendered the design non-functional on the FPGA. Due to the error that we discussed earlier, regrettably we were not able to successfully implement this design on the FPGA. However, we have undertaken extensive simulation and testing to verify that this module functions as it is designed. So we see here a number of signals, the I/O signals from the top-level module, some of the key ones. We see the cathode and anode signals driving the 7-segment display. We see the time output of the stopwatch, the present and next states of the stopwatch, and the max time register from which the stopwatch counts down. The importance of this signal is that it is necessary to verify that the stopwatch's program functionality is working correctly. As discussed earlier, this is a clock-driven state machine, our stopwatch is. So its states change every clock cycle depending on the inputs. The first high signal pulse we see here is the up signal. When this signal is high, the stopwatch counts up. Every second clock cycle, it increments its time count by 2 cycles or 20 nanoseconds. The next signal pulse we see here is the start-stop signal, which turns on the stopwatch. After this signal goes high, we see a delay of a few positive clock edges, which correspond to state machine transitions that take the machine from the start to the running mode. And on the third positive clock edge, we indeed see here that the time signal is incrementing by 2. And equally, the changes in the present and next state demonstrate the state machine cycling through the necessary states to get to the count up mode. Moving forward now, we see that the 7-segment display signals, the anode and the cathode, are changing in response to the change in time in the stopwatch. We see that as designed, a subsequent start-stop signal on a positive clock edge will pause the stopwatch. It pushes that stopwatch state machine into a state where it no longer increments the count and waits for further signals before resuming counting. This continues until the reset signal goes high. This causes the state machine to transition to an idle state in which its output is 0. Therefore, the time displayed on the 7-segment display would be 0 seconds following the reset signal, as long as the up signal is high. Now we see this start-stop functionality for a few more states, but what is of interest here is when the up signal goes low, the stopwatch switches mode. We see every positive clock edge. The states are transitioning, and we arrive in the idle state where the machine is prepared to count down from a hard-coded time. This here is 590 million or 59 seconds, the hard-coded time from which we've chosen to count down. Now, this will sit in the idle state until the start-stop signal goes high. At the subsequent positive clock edge, we see a state transition into the counting state, which then transitions into an incrementing state, and accordingly, we see the time decrementing in intervals of 2 per 20 nanoseconds. And the entire time, the anode and cathode signals are changing as the time signal passed into the 7-segment display decoder and the BCD decoder are changing, which therefore suggests that the cathode and anode are appropriately displaying the stopwatch values on the board. The final functionality to demonstrate here is the program mode of the stopwatch. When this signal goes high, at the positive edge of the clock, the state machine will transition to the state encoded here as 2, or the binary digit 10. This state is where the user sets the max time register to the value they wish to count down from. At every pulse of the increment signal on the positive edge of the clock, while the program signal is high, we see that the max time is incremented. The size of the increment depends on the minute signal here. If the minute signal is high, it will add 600 million, corresponding to, pardon me, that is 6 billion, which corresponds to 1 minute. And here, a pulse of the increment signal, when the minute signal is low, adds 1 second, or 1 billion. And this here is a comprehensive demonstration of our stopwatch functionality.
So shown here is the functionality of the simulation for the leaderboard module. So the way it works is obviously you have a time in input. Here, for example, it's 5. Right now the stopwatch mode is in mode 1 and the display mode is in 4. How this essentially works is that it's going to be displaying the top score of the slow mode, which would be 5 in this case because right now it's in that slow mode. Also, what we see here is because the first rank changes, top score, number 1, the signal will change. As you can see here, when there's a different change in input, when you input 6, you will see it rise to a high signal. And you will also see the corresponding timeout because it's in the default mode of display 0.
All right, so here is the 7-segment display running. As you can see, it's already been running for a little bit, but it's been counting up at a rate of 1 second per second. And just 5 seconds right here, you can see it's going to roll over. And yeah, it goes seconds, milliseconds, and minutes.
So they're switched.
I don't know what's going on. Like, no, this is right. This is, look at numbers. This is 50 and BC. Like, we're getting it somehow. I don't know what's going on. But the point is, you're like, if I check